Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University. Today, we are going to discuss about the module Classical System of Interacting Particles Part 1, which involves modal potentials, hard sphere gas, van der Waals equation of state from paper Statistical Mechanics. This module, Classical System of Interacting Particles Part 1, has been developed for postgraduate level as per the following subtopics. Modal potentials, which include hypothetical modal potential, hard sphere potential, Square-Well potential, Lenard-Jones potential. In hard sphere gas, we will look at the Hamiltonian and configurational integral, one-dimensional hard sphere gas, its exact solution, and generalization to higher dimensions, and calculate thermodynamic properties. A gas with attractive interaction of finite range. Using classical perturbation theory, we will calculate partition function and find first order correction to free energy. Van der Waals equation of state, we will draw its isotherms and understand Maxwell construction. So students, let us see what we are going to learn in this module. We will try to understand how an ideal gas equation gets modified when interaction among the particles of the gas gets included. We will also appreciate the possible interaction potentials which can be modeled to include interaction limited to two-particle interaction featuring attractive part and repulsive part, two essential features of a real system. We will try to understand features of a hypothetical model, potential, hard sphere potential, Square-Well potential, and very well known Lenard-Jones potential. We will derive for a hard sphere gas partition function made up of momentum integral and configurational integral. We will derive for an exactly solvable one-dimensional hard sphere gas partition function and free energy, and generalize the result to higher dimensions and calculate partition function and free energy. We will derive using classical perturbation theory first order correction to free energy of an ideal gas by a weak two-particle attractive potential. We will derive van der Waals equation of state starting from free energy of a gas with realistic repulsive potential modeled by a hard sphere and realistic weak attractive two-particle potential. Express van der Waals equation of state in dimensionless form, making it independent of system parameters. Appreciate various features of the isotherms of van der Waals gas equation at critical temperature Tc for T greater than Tc and for T less than Tc, and identify the limitations of slopes of the isotherms below Tc. We will try to understand how the limitation of positive slope parts of isotherms below Tc was overcome by Maxwell's construction and get a plausibility argument to arrive at Maxwell's equal area law using Gibbs energy formula at constant temperature and understand how it points to gas-liquid transition. So, let us try to go beyond ideal gas systems. In this module, we make a departure from looking at ideal systems alone. In an ideal gas system, the density of the system is very low that particles are so far apart that interaction among the particles is negligible. We wish to look at the real systems or the so-called non-ideal gases restricting to classical systems only. As the density increases, the particles start coming closer to each other and interactions no longer remain negligible and ideal gas equation of state no longer remains valid. Therefore, our main focus will be to see how ideal gas equation of state gets modified as a result of such an interaction. In fact, number of empirical and semi-empirical equations of states have been proposed for non-ideal gases, the most famous being Van der Waals equation of state after the name of Dutch physicist Vander Waal, which met with a reasonable success to explain qualitatively the behavior of real gas systems near the gas-liquid critical point. Later, Thiessen proposed and Kamerlingh-Onnes carried the study forward, providing a very strong theoretical background, and proposed the virial equation of state as an infinite power series in terms of number density n upon v, which is P upon kBt is equal to n upon v plus B2 as a function of t multiplied by n upon v whole square plus B3t multiplied by n upon v whole cube plus so on. The quantities B2 as a function of t, B3 as a function of t, and so on are called the second, third, and so on virial coefficients respectively, which depend only on temperature and are independent of pressure and density. The jth virial coefficient in fact corresponds to inclusion of j particle interactions in a given volume V. To prepare for understanding classical systems with interaction, we first have a look at some possible interaction energy forms, or the so-called model potentials. This will be followed by detailed study of a hard sphere gas to calculate the partition function in terms of configurational integral solved for one-dimensional case and further generalized to higher dimensions by method of induction to obtain free energy. This will be supplemented further by introducing weak attractive interaction to calculate by perturbation method free energy. The two results together shall be used to derive well-known van der Waals equation of state for a real gas whose isotherm shall be plotted to identify its limitations and remedy these by introducing the well-known Maxwell's construction and understanding of gas-liquid transition. Model potentials. In literature, number of model potentials which were proposed from time to time were supposed to take care of two broad features expected in the real behavior of atoms in gases. First, at very short distances, potential should be such that atoms at such distances should not sit on top of each other, demanding a repulsive part. And second, at moderate distances, it should allow for keeping the atoms together, ultimately going to zero at large distances. In the following model potentials, we will see this reality being introduced. Out of these model potentials, because of some very empirical reasons, some potentials emerge to be favorites for making theoretical studies of interacting classical systems. Let us have a look at few of these. Hypothetical model potential. A typical hypothetical interparticle potential VR is given in the plot below in figure 1. It is showing a strongly repulsive part with a weak attractive well. Its shape depends upon the structure of the molecules. R is the molecular distance. A very large number of model potentials are available in literature to be as closer to real potentials as possible. Hard sphere potential. The hard sphere potential is represented mathematically as phi r is equal to infinity for r less than sigma and equal to 0 for r greater than sigma. Graphically, it is shown in figure 2. This potential has repulsive part only and no attractive part, yet very closely represents the steep repulsive parts of realistic potentials. It is the simplest potential and therefore analytically tractable to calculate virial coefficients up to 7th order. A gas modeled on this potential is called hard sphere gas or fluid. Square-well potential. Square-well potential is an improvement over hard sphere potential with the inclusion of an attractive part, keeping it analytically tractable. It has the form phi r is equal to infinity for r less than sigma is equal to minus epsilon for sigma less than r less than lambda sigma and 0 for r greater than lambda sigma, where Lambda is the range of attractive potential whose depth is minus epsilon. Graphically, it can be visualized as given in figure 3. This Scarewell potential has a range sigma and depth epsilon. Lenard-Jones potential. The Hart sphere and Scarewell potentials are nowhere closer to the hypothetical potential and are very far from actual interparticle potential. Lenard-Jones potential is the closest to the hypothetical potential, which qualitatively represents the desirable behavior. It has an attractive part with an appropriately incorporated short distance repulsive part. It is also called 612 potential and algebraically has the following form. Phi r is equal to 4 epsilon multiplied by sigma upon r raised to power 6 minus sigma upon r raised to power 12. It has a minimum at r is equal to sigma. In fact, Lenard-Jones potential has been chosen out of a generic potential called Nm potential, represented by the form phi r is equal to 4 epsilon multiplied by sigma upon r raised to power n minus sigma upon r raised to power m, where m is less than n. After it was found that n is equal to 6 and m is equal to 12 represents the best approximation for most of the cases. Also, it must be emphasized that it is a two-body potential and neglects three-body and higher number of bodies interactions. The attractive part is a result of each particle, that is atom or molecule, treated as a dipole, resulting in an attractive potential with power 6. This potential indeed represents the van der Waals force between the two particles. R raised to power 12 repulsive term is a result of Pauli's repulsion at short ranges due to overlapping atomic orbitals. 612 potential is plotted in figure 4. One can see that the minima of the potential occurs at r is equal to 2 raised to power 1 upon sigma and depth of the minima is epsilon. Lenard-Jones potential has been used extensively to study many properties of solids, liquids and gases successfully. In this course, our interest is to look at interacting systems described by the model potentials described above only, though there are a large number of model potentials discussed in literature tailored to meet particular needs. Hart sphere gas. As stated earlier, a Hart sphere gas is a system in which a gas is modeled on Hart sphere potential. It implies that gas is made up of particles, atoms or molecules such that their radius is unaffected by any external influence such as change in temperature, pressure or collision among each other. The closest distance sigma the two particles can come is when the distance between the centers of two Hart spheres is equal to the diameter of the sphere, that is 2 times the radius of the sphere r0 as shown in figure 5. Also from the plot of the Hart sphere potential, it is clear that for distance greater than sigma, there is no interaction between the particles. Now we look at the Hamiltonian and configurational integral of an n-particle gas system. Let us denote the position of the centers of spheres constituting the system by position vector Ri, where I goes from 1 to n. The Hamiltonian of the system can be written as H is equal to H ideal plus phi as a function of R1 up to Rn, where H ideal is equal to sum over I pi square upon 2m is the Hamiltonian corresponding to the ideal gas, and phi R1 so on up to Rn is the Hart sphere potential energy given by phi R1 up to so on up to R2 is equal to infinity for modulus of Ri minus Rj less than sigma and 0 for modulus of Ri minus Rj greater than sigma. Since we are assuming only two particle interactions, seventh can also be written as equal to summation over I greater than j, summation over j phi 2 as a function of modulus of Ri minus Rj, where phi 2 as a function of Ri minus Rj is equal to infinity for modulus of Ri minus Rj less than sigma and is equal to 0 for modulus of Ri minus Rj greater than sigma. With the Hamiltonian given by 6, the partition function of the system can be written as Qn Vt is equal to 1 upon n factorial h raised to power dn integral over e raised to power minus beta summation over I pi square upon 2m minus beta summation over I is greater than j, summation over j, phi 2 as a function of modulus of r minus rj, d dn p d dn r. Here n is the number of particles and d is the dimension of the system. Factor n factorial comes because of indistinguishability of the particles in the system. Obviously now 10 can be written as equal to 1 upon n factorial h raised to power dn integral over e raised to power minus beta summation over I pi square upon 2n d dnp integral over e raised to power minus beta summation over I is greater than j, summation over j, phi 2 as a function of modulus of Ri minus Rj d dnr. Here decoupling the momentum part and position part has happened, and hence momentum integral can be solved easily given by 2 pi m kt raised to power dn divided by 2. Recalling that h upon 2 pi m kt raised to power half is equal to lambda, the mean thermal de Broglie wavelength. 11th can be written as Qn as a function of V and T is equal to 1 upon n factorial lambda raised to power dn integral over e raised to power minus beta summation over I is greater than j, summation over j, phi 2 as a function of modulus of Ri minus Rj d dnr. Here the remaining integral is over the space coordinates of the n particles only and is called configurational integral, represented by Zn as a function of V and T such that Zn as a function of V and T is equal to integral of e raised to power minus beta summation over I is greater than j, summation over j, phi 2 as a function of modulus of Ri minus Rj d dnr. For the ideal gas, phi 2 as a function of Ri minus Rj is equal to 0, so that Zn ideal as a function of V and T is equal to V raised to power n, and the configurational integral for an ideal gas, that is Qn ideal as a function of V and T, is equal to V raised to power n divided by n factorial lambda raised to power dn, as is the case. In the case of interacting non-ideal systems, main task is to calculate the configurational integral. One-dimensional hard sphere gas exact solution. Formulation of a one-dimensional hard sphere gas containing n particles confined linearly over a length L can be visualized as placing spherical beads of radius R0 on a wire of length L, as shown in the figure 6 below. Here each bead is of radius R0 distributed over a wire of length L. Note that from the either edge of the wire, a bead cannot be positioned with its center at a distance less than the radius R0 of the bead. Secondly, the length L of the wire must be greater than n times 2R0. So the problem of evaluating configurational integral can be built up inductively as follows. For a hard sphere gas containing only one sphere confined over a length L, configurational integral can be written as Z1 as a function of L and T is equal to integral from R0 to L minus R0 dx1 is equal to x1 with limits from R0 to L minus R0, which is equal to L minus 2R0. We can write this alternately. Suppose that wire's left end is positioned at A and right end at B. Then length of the wire is equal to B minus A, and therefore 14 can be written as Z1 as a function of L and T is equal to Z1 as a function of A, B and T is equal to B minus A minus 2R0. To proceed further, we state an ansatz that for distributing n particles over the wire of length L, the configurational integral Zn as a function of ln t is given by Zn as a function of A, B and temperature T is equal to B minus A minus 2R naught multiplied by N and whole raised to power N. And to prove the above assumption, we apply method of induction, according to which if we take n is equal to 1, it is obviously true, and if it can be proved true for n is equal to n plus 1, the stated ansatz can be established as true. Proving this amounts to adjusting one more particle on the wire. Let us assume that it is positioned at k plus 1, the position denoted by x, such that there are k particles towards left and n minus k particles towards right, where k can take any integer value between 0 and n. The net configurational integral for adjusting k plus 1 particle can be written as a sum over all the configurational integrals, with each term weighted by the factor counting the possible ways of selecting k particles towards left of k plus 1 particle out of a total of n particles, which is given by the combination nk. That is, you are putting k particles over a length bounded by 0 to x minus r naught and n minus k particles over a length bounded by x plus r naught, comma L. Thus we can write Zn plus 1 is equal to summation over k is equal to 0 to n binomial coefficient nk integral from x minimum to x maximum zk as a function of 0 to x minus r naught multiplied by Zn minus k as a function of x plus r naught, comma L. For the sake of simplicity, we have omitted t. Using the ansatz 16, we can rewrite 17 as Zn plus 1 is equal to integral from x minimum to x maximum multiplied by summation over k is equal to 0 to n combination k, x minus 2k plus 1 r naught raised to power k multiplied by L minus x minus 2n minus k minus 1 whole raised to power n minus k dx. Recalling binomial theorem for a positive integer, x plus a raised to power n is equal to summation over k is equal to 0 to n binomial coefficient nk x raised to power k a n minus k can be written as Zn plus 1 is equal to integral from x minimum to x maximum over L minus 2 times n plus 1 r naught whole raised to power n dx, which is equal to L minus 2n plus 1 r naught whole raised to power n multiplied by integral from x minimum to x maximum over x. Now let us look at the limits of x. K particles are distributed over a distance k times 2 r naught plus r naught, so that x minimum is equal to 2k plus 1 r naught, and n minus k particles must be distributed over a distance to accommodate n minus k particles. That is, n minus k into 2 r naught plus r naught, which is equal to 2 times n minus k plus 1 multiplied by r naught, so that x maximum is equal to L minus 2 times n minus k plus 1 multiplied by r naught. Using these limits, the integral yields x maxima minus x minima is equal to L minus 2 times n plus 1 r naught, so that we find that Zn is equal to L minus 2 times n r naught whole raised to power n, provided n is an integer less than L upon 2 r naught, and the partition function is then given by Qn as a function of ln t is equal to L minus 2 times n r naught raised to power n divided by n factorial lambda raised to power n. The free energy of the one-dimensional hard sphere can now be obtained as A is equal to minus Boltzmann constant multiplied by temperature log of Qn as a function of ln t is equal to minus n kBt multiplied by log of L minus 2 n r naught divided by n lambda plus 1. Generalization to higher dimensions and thermodynamic properties. Let us look at some interesting features of the configurational integral 21 derived for a one-dimensional hard sphere gas. For R0 is equal to 0, configurational integral reduces to L raised to power n. Effective length available is L minus 2 times n R0. This suggests that for a higher dimensional case, say dn is equal to 3, say L should get replaced by V raised to power n for R0 is equal to 0, and for a hard sphere gas should lead to an effective volume V should get replaced by V minus Bn, where B has the dimensions of volume and is a function of the radius R0 of the sphere. Thus, for a system of higher dimensions, the configurational integral can be written as Zn is equal to V minus Nb raised to power n. For R0 is equal to 0, B is equal to 0, and therefore configurational integral reduces to V raised to power n. Hence, partition function for the hard sphere comes out to be Qnvt is equal to V minus Nb raised to power n divided by n factorial lambda raised to power n. Now we can obtain free energy. A is equal to minus kBt log of Qn as a function of V and t is equal to minus n kBt multiplied by log of V minus Nb divided by n lambda plus 1. Putting V is equal to 0 yields the same result which we obtain for an ideal gas. Nb is the consequence of the hard sphere potential. Since because of the finite size of the spheres, all the volume is not accessible to the hard spheres, the closest distance to which the centers of two spheres can come cannot be less than 2r0. A gas with attractive interaction of finite range. Let us move from a hard sphere gas to a gas among whose particles there is a finite range weak two-body interaction potential, defined by phi r1 so on up to r2 is equal to minus epsilon comma 0 for modulus of Ri minus Rj less than sigma and is equal to 0 for modulus of Ri minus Rj greater than sigma, where sigma is the range of interaction. The Hamiltonian of this problem can be written as H is equal to H ideal plus H1, where H1 is equal to summation over I greater than j, summation over j, phi 2 as a function of Ri minus Rj. When phi 2 as a function of modulus of Ri minus Rj is equal to 0, the system reduces to an ideal gas. Classical perturbation theory, calculation of partition function. It is a well-known theory in classical or quantum mechanics. This can be applied if Hamiltonian of a system can be written as sum of two terms, with first term usually denoted by H0 and the second term H1, a very small term compared to H0 called perturbation. That is, H is equal to H0 plus H1 and H0 is very much greater than H1. Then if the partition function can be evaluated exactly for H0, further correction to the partition function because of perturbation H1 can be evaluated systematically by what is called perturbation expansion procedure. We rewrite 29 by making smallness of H1 explicit by introducing a small parameter lambda such that H is equal to H0 plus lambda H1 dash. Perturbation expansion is indeed a power series in terms of this parameter lambda, which gives exactly soluble part when put equal to 0. Now for the partition function, we can write log of z as a power series. Log of z is equal to log of z0 plus lambda times derivative of log of z with respect to lambda at evaluated at lambda is equal to 0 plus lambda square by 2 multiplied by second derivative of log of z with respect to lambda evaluated at lambda is equal to 0 plus so on. Once again it is emphasized, when lambda is equal to 0, we get partition function for the unperturbed part of the Hamiltonian, H0. This is the part which can be evaluated exactly and is a requisite for the perturbation expansion to be applicable. Using the notation of quantum mechanics, to apply 29, let us look at the partition function z is equal to trace over e raised to power minus beta h is equal to trace over e raised to power minus beta multiplied by h naught plus lambda h1 dash. Classically, trace means integration over whole of the phase space divided by suitable power of 2 pi h bar. Using 32, derivative of log of z with respect to lambda is equal to 1 upon z, derivative of z with respect to lambda is equal to 1 upon z, derivative of trace of e raised to power minus beta h naught plus lambda h1 dash with respect to lambda is equal to 1 upon z, trace of minus beta h1 dash e raised to power minus beta h naught plus lambda h1 dash. Recalling the definition of expectation value of an operator O, which is equal to trace of operator O e raised to power minus beta h divided by trace of e raised to power minus beta h is equal to trace of operator O multiplied by e raised to power minus beta h divided by z gives the derivative of log of z with respect to lambda is equal to expectation value of minus beta h1 dash, which is equal to minus beta expectation value of h1 dash. Since we require derivative of log of z with respect to lambda evaluated at lambda is equal to 0, the expectation value has to be evaluated with lambda is equal to 0, that is with the Hamiltonian h naught such that derivative of log of z with respect to lambda evaluated at lambda is equal to 0 is equal to minus beta expectation value of h1 dash corresponding to lambda is equal to 0. Similarly, we can evaluate the second order derivative as second order derivative of log of z with respect to lambda is equal to d upon dz multiplied by 1 upon z dz by d lambda, which is equal to 1 upon z d2z by d lambda square minus 1 upon z into dz by d lambda whole square, which is equal to 1 upon z trace of beta square h1 dash square e raised to power minus beta h naught plus lambda h1 dash minus 1 upon z trace of minus beta h1 dash e raised to power minus beta h naught plus lambda h1 dash whole square, which is equal to beta square multiplied by expectation value of h1 dash square minus beta square multiplied by expectation value of h1 dash square. Once again, since we require the second order derivative of log of z at lambda is equal to 0, the expectation value has to be evaluated with lambda is equal to 0, that is with the Hamiltonian h naught such that second order derivative of log of z with respect to lambda is equal to beta square multiplied by expectation value of h1 dash square evaluated at lambda is equal to 0 minus expectation value of h1 dash evaluated at lambda is equal to 0 square. Thus, up to the second order correction, we have log of z is equal to log of z0 minus lambda beta expectation value of h1 dash evaluated at 0 plus lambda square by 2 beta square multiplied by expectation value of h1 dash square minus expectation value of h1 dash evaluated at lambda is equal to 0 square. Recalling h1 is equal to lambda h1 dash, or log of z is equal to log of z0 minus beta h1 evaluated at lambda is equal to 0 plus beta square by 2 multiplied by expectation value of h1 square evaluated at lambda is equal to 0 minus expectation value of h1 evaluated at lambda is equal to 0 square plus so on. Similarly, we can evaluate the higher order terms. First order correction to free energy of an ideal gas perturbed by a weak attractive interaction. Now we are ready to evaluate first order correction to partition function of an ideal gas perturbed by a very weak finite attractive interaction defined by equation 28. Thus, expectation value of h1 evaluated at lambda is equal to 0 is equal to 1 upon v raised to power n multiplied by e raised to power minus beta h0 d3np summation over I greater than j summation over j integral of d3np integral of d3n over r phi 2 as a function of modulus of Ri minus Rj multiplied by e raised to power minus beta h0. Summing over I and j gives terms which are n times n minus 1 divided by 2 in number and give the same contribution. Therefore, 41 can be written as expectation value of h1 evaluated at lambda is equal to 0 is equal to n times n minus 1 upon 2 multiplied by v raised to power 1 integral over d3n r phi 2 as a function of modulus of Ri minus Rj, which is equal to n times n minus 1 divided by 2 raised to power vn multiplied by v raised to power n minus 2 integral of d cube r1 integral of d cube r2 phi 2 as a function of r1 minus r2, where v raised to power n minus 2 factor comes from all other coordinates except r1 and r2. Put r is equal to r1 and r1 minus r2 for fixed r1, dr is equal to dr2. Hence, expectation value of h1 evaluated at lambda is equal to 0 is equal to n times n minus 1 divided by 2 v squared integral of 4 pi r1 squared dr1 integral of 4 pi r2 squared dr2 phi 2 as a function of modulus of r1 minus r2 is equal to 4 pi n into n minus 1 divided by 2v square into v multiplied by integral of phi 2r with respect to dr2. For n large, this can be written as expectation value of h1 evaluated at lambda is equal to 0 is equal to n square upon v 2 pi times integral from 0 to infinity r2 square dr2 phi 2r. Let us look at the integral in 45. Since phi r2 as defined in 27 is negative and phi naught, integral must be negative, say minus a upon 2 pi. That is, expectation value of h1 evaluated at lambda is equal to 0 is equal to minus a n raised to power 2 divided by v. So, the free energy of the perturbed ideal gas by an attractive potential can be written as A is equal to minus Boltzmann constant Kb multiplied by temperature T log of Qn as a function of V and T is equal to minus n kBt log of V upon n lambda plus 1 minus a n square upon V. Van der Waals equation of state. Now, with the treatment of the ideal gas in the presence of repulsive three-dimensional hard sphere potential and a weak attractive potential, we can go ahead with the discussion of bringing these two together, which is the case in real systems, by combining together the attractive and repulsive part contributions to the free energy as given in 26 and 47. The effective potential shown in figure 7 is the schematic representation of hard sphere potential with weak attractive part. Then A is equal to minus kBt log of Q as a function of V and T is equal to minus n kBt log of V minus Bn divided by n lambda plus 1 minus a n square upon V. We can derive expression for the pressure P from 48. We know pressure P is equal to negative of the partial derivative of A with respect to V at constant T and N, which is equal to N multiplied by Boltzmann constant Kb absolute temperature T divided by V minus Bn minus A times N square divided by V square. This is the famous Van der Waals equation of state for a real gas arrived at by famous Dutch physicist Johannes van der Waal, who believed in the molecular theory of matter and imagined a gas to be made up of molecules of finite size and that there is an attraction between these molecules. The biggest success of Van der Waals equation of state was that it not only explained the deviation from the ideal gas law, but also provided a reasonably correct description of the system near the gas liquid critical point and played a crucial role in understanding liquefaction of gases and phase transitions. Isotherms of Van der Waals equation of state. To appreciate the full consequences of Van der Waals equation of state, it will be interesting to look at pressure versus volume plots for different fixed temperatures called isotherms. Conventionally, these isotherms are plotted between small p, which is a ratio of P upon Pc, and small v, which is a ratio of V upon Vc for different t's measured in the units of Tc, that is, corresponding to small t is equal to T upon Tc. Here, capital PC, capital Vc, and capital Tc are respectively the critical pressure, critical volume, and critical temperature, which we look at after analyzing general features of the isotherms plotted in figure 8. Here we note that the red curve corresponds to the region where all isotherms have wrong sign, that is positive, of the slopes. It is obvious from figure 8 that above t is equal to 1 curve, that is for t greater than Tc, curves have the shape of ideal gas isotherms, but below t is equal to 1, that is for t less than Tc, slopes of the curves for certain values of volume and pressure become negative, which is an unphysical situation. Also, stability condition demands that the slope of the curve should always be negative, which is not true for some range of values of volume shown by drawing a curve joining the points where slopes vanishes. Condition for the vanishing of the slope is given by partial derivative of P with respect to V at constant temperature equal to minus n Boltzmann constant multiplied by T divided by V minus Bn whole square plus 2 times a n raised to power 2 divided by V cube should be equal to 0. For a given value of V, this condition is satisfied for a particular temperature called critical temperature Tc, given by Tc is equal to T is equal to 2 times a times n times V minus B n raised to power 2 divided by n times Boltzmann constant V raised to power 3. Substituting the value of T in 48, we get pressure is equal to 2 times AB n raised to power 3 divided by V cube plus A times n raised to power 2 divided by V square. A curve joining the points of zero slope on the isotherms is shown in figure 8. The top of this curve touches the isotherm corresponding to Tc, called the critical temperature, signifying the fact that isotherms above this point all have negative slopes. Below Tc, slope of typical isotherms crossing the curve becomes 0, then becomes positive and continues to be positive till it crosses the right boundary of the curve. On the left and right boundaries of the curve, the second order derivative, that is partial derivative of P with respect to V, that is second order at constant temperature, is therefore respectively greater than 0 and less than 0. As the temperature rises, the two boundaries merge till the curvature becomes 0 at T is equal to Tc. This implies that at T is equal to Tc, both partial derivative of P with respect to V at constant temperature and second order partial derivative of P with respect to V at constant temperature vanish, corresponding to pressure and volume at this point representing critical volume Vc and critical pressure Pc. Equation 51 and the condition that the partial derivative of P with respect to V second order at constant temperature is equal to 0, leading to second order partial derivative of P with respect to V at constant temperature is equal to 2 times n times Boltzmann constant times temperature divided by V minus B times n whole cube minus 6 times A times n square divided by V raised to power 4 is equal to 0, which can be used together to calculate Vc. Once Tc and Vc are known, Pc can be calculated by putting these values in equation 50. Following this procedure, one gets Vc is equal to 3Nb, Tc is equal to 8A upon 27 times B times Boltzmann constant, and Pc is equal to 2 upon 27 B square. Expressing P, V and T in the units of PC, VC and TC with small p is equal to P upon PC, small v is equal to V upon VC and T is equal to T upon TC as dimensionless variables, the van der Waals equation of state becomes small p is equal to 8 times small t divided by 3 times small v minus 1 minus 3 upon small v square. Equation in this form is a universal equation in the sense that it does not depend on the system parameters A and B explicitly, implying that units can be chosen for each system in such a way that form of the relation remains unchanged. Maxwell construction. The two problems discussed in the case of van der Waals isotherms, namely, for T less than Tc, slopes of the curves for certain values of volume and pressure become negative, which is an unphysical situation. Stability condition also demands that slope of the curve should always be negative. Need to be sorted out. Solution to these problems are provided by Maxwell construction. To clarify the situation, let us look at an isotherm of a typical gaseous system above Tc and below Tc as shown in figure 8. Let us look at above Tc first. For an isotherm of a gaseous system above Tc, let us decrease the volume. We notice that as volume decreases, pressure decreases, and we move smoothly from right hand side of the curve to the left hand side of the curve. Below Tc, it will be nice to explain using a water as an example. Water has critical temperature of 647 K. Let us pick this water system at temperature below Tc, but slightly above its boiling point, say 373 K. Also say the pressure is atmospheric pressure. Temperature of the vapor is higher than the boiling point of water at this pressure. Now, as we decrease the volume, pressure increases, simultaneously leading to increase in boiling point of water, and hence condensation point is also higher. So, as pressure increases, water vapors start condensing. Since water occupies a much smaller volume on condensation for the same mass of water vapor, so when we try to decrease the volume further, some vapor will condense, further keeping the pressure constant. This implies that isotherms must have a horizontal region in the middle as shown in figure 9. For a given temperature at this pressure, liquid and water vapor coexist. When whole of the water vapors get condensed, to decrease the volume further, one needs to apply a very large pressure with a consequent steep rise in the isotherm. But what is the value of this constant pressure in the coexistence region described above? Maxwell provided an answer to this in the so-called Maxwell construction, which effectively means drawing a horizontal line below Tc, cutting the isotherms at 3 points enclosing two bounded areas, one below the horizontal line on the left and the other above the horizontal line towards the right, and coexistence occurs at that pressure when the areas of these bounded regions become equal, resulting in a modified isotherm with a horizontal part. Hence, there is now no part of the isotherm with positive slope and hence satisfies the stability criteria. Let us look at figure 9 carefully. Part of the isotherm, that is from delta to gamma, corresponds to liquid phase. Part of the isotherm beta to alpha corresponds to gas phase. Part from gamma to beta corresponds to coexisting phase of liquid and gas states. Lowest volume intersection of the horizontal line with the isotherm gives volume of the liquid phase and the highest volume intersection gives the volume of the gas phase. Justification of Maxwell construction. To justify the Maxwell's equal area construction idea further, let us recall the formula for Gibbs free energy at constant temperature, that is dG is equal to V times dP. Integrating equation 56 along the isotherm figure 9 from alpha to beta with integration over pressure, the vertical axis, we have integral from alpha to beta over dG is equal to G beta minus G alpha is equal to integral from alpha to beta over V dP, or G beta minus G alpha is equal to integral of alpha to beta of V dP. Thus, If A2 is greater than A1, then G gamma is greater than G beta, and beta will be the stable equilibrium. Otherwise, if A1 is greater than A2, then G gamma is less than G beta, and gamma is the stable equilibrium. If A1 is equal to A2, then the two phases can coexist in equilibrium. This is also known as Maxwell's equal area law. The most important success of the van der Waals equation of state, which included attractive and repulsive part of the interaction between gas molecules, lies in the prediction of gas-liquid transition. So students, let us summarize what we have learned in this module. We learned that a typical gas can be treated as an ideal gas as long as density is low. As density of the gas becomes large, as is the case in real gases, interaction among the particles comes into play, leading to a departure from ideal gas behavior. We learned that interaction among the particles of the gas can be modeled by suitably chosen two-particle potentials. We learned about the typical features of a hypothetical interaction potential, mimicking both attractive and repulsive interaction components. We learnt about following three model potentials and their properties. Hart sphere potential, phi r is equal to infinity for r less than sigma, 0 for r greater than sigma. Scale-well potential, phi r is equal to infinity for r less than sigma, minus epsilon for sigma less than r less than lambda sigma, is equal to 0 for r greater than lambda sigma. And the famous Lenard-Jones potential, phi r is equal to 4 times epsilon multiplied by sigma upon r raised to power 6 minus sigma upon r raised to power 12. We learned that Hart sphere gas as a model interacting real gas can be used for calculating its partition function and configurational integral. We learned how to exactly solve one-dimensional Hart sphere gas for its configurational integral by method of induction and obtain partition function and free energy of this system. We also generalized one-dimensional Hart sphere gas to three-dimensional Hart sphere gas and explicitly obtained free energy of the system, showing the consequence of finite size effect compared to ideal gas. We learned how to model real gas with weak attractive interaction and to calculate its partition function using classical perturbation method and hence obtain first order correction to free energy. We learned that from the knowledge of the free energy of a gas with two particle Hart sphere repulsive potential and a weak attractive potential, we can obtain van der Waals equation of state, namely pressure is equal to N times Kb multiplied by T divided by V minus Bn minus A times N square divided by V square. We learned that the isotherms of van der Waals equation of state above critical temperature are ideal gas-like, whereas below the critical temperature have some unphysical features. We learned how to obtain van der Waals equation of state in dimensionless form independent of system parameters, namely small p is equal to 8 times t upon 3v minus 1 minus 3 upon v square, where small p is equal to capital P upon Pc, where Pc is critical pressure, small v is equal to capital V upon Vc, where Vc is critical volume, and small t is capital T upon critical temperature. We also learned how Maxwell's construction on the isotherms of van der Waals equation results in overcoming the limitations of positive slope of the isotherms below Tc and settling the violation of stability criteria. We learned that Maxwell's horizontal line corresponds to region of coexistence of liquid and gaseous phases in equilibrium and is placed such that area enclosed by the line by it below the isotherm and above the isotherm are always equal, called Maxwell's equal area rule. Effectively, Maxwell's construction pointed towards gas-liquid transition. Thank you.